Hello, Disobey.
Hello.
Um, Thanks for staying this late, but the party's starting after this, so get ready for it. My name is Cesar,
And I'm Nicola.
and we are here from the former Tampere University of Technology. Now it's Tampere University, in case you didn't know. And it's all purple and nice. It's just a coincidence that it matches the Disobey theme. But anyway, we are here to talk about Super Smash Bros. Ultimate. So you may wonder what it is about. We are about to disappoint you. This is not how to hack the game. This has nothing to do with the game and a lot to do with hacking. So
It was just a catchy title.
yes, it's clickbait. So okay, so I promise it will be easy, but for now, just go on with me. So we have Port Smash. I don't know if you have heard of Port Smash. Hopefully some of you have. Port Smash is a microarchitecture attack technique that abuses the execution units by exploiting port contention in order to create a high-resolution timing side channel capable of leaking information from secret-dependent algorithms. So that's a mouthful. Sorry. So we're going to break it into different topics so that it's easier for you to follow and easy for us to explain. So first of all, we are going to talk about what a side channel is, because that's the basis of our talk. And I know many of you might be already acquainted with the term side channel, but some of you might not, even though we use it now, and the previous presenter also talked about or mentioned side channels briefly. So for that, I'm going to talk a little bit of the history, how they were discovered. So in the 40s, there was this scientist working at Bell Laboratories, and he was working with this old 131B2 machine that was used to encrypt communications and was used during the war to help US. So he was fiddling with the machine at his lab, and then he noticed that somewhere far in the room, in the lab, there was an oscilloscope. And that every time he pressed a key on the machine, there was a spike on the oscilloscope. And then he started thinking, why is this happening? It makes no sense. So he started looking into it, and then he discovered that was a correlation between the key that he pressed and the spike on the oscilloscope. So basically, he could, in a way, see secret information or what was being written just by looking at the oscilloscope. So this was during the war. He went with the superiors and he told them, okay, we have this issue. We know we promised a very secure machine, but now we have this one and we can recover information from it. And then the official said, okay, this sounds very esoteric, so go and make tests. And when you know for sure, then come back to us. And he did that. Soon he returned to the officials, and he proved that he could recover at least 75% of what was written on using this machine. So they were very worried about it, but it was war times, so they couldn't afford just to get all the machines back, fix them, and then put them again. So what they did, they said, okay, try to make an enclosure for it so it can protect against these leakages, but we are not removing any of these from wherever they are. And that's what he did, but he took 6 months to do this. And then the enclosure was big and make things complicated. So at the end, the officials decided not to use it and instead just, okay, we're going to defend 100 feet around whenever we use one of these machines so nobody can spy on this. And that's what they did. After that, the war ended and everybody forgot, well, people forgot about, the researchers forgot about this phenomenon. And later, during the 50s, the CIA noticed that this was happening, and then they went back to Bell Laboratories, and then they heard about these scientists who have found this before. And on top of that, they discovered that it's not only electromagnetic emanations that were being recorded by the oscilloscope, but also the audio of each key was different, so they could use the audio to recover secret information. Starting from that, they created this regulation that was called Tempest, in where they gave instructions how to build machines to prevent the leakage of secret information. So there were Tempest-proof or Tempest-approved machines by the government that should be used in the military. After that, it continued to be used and be a topic only for the military. But during the 60s and the 70s, but then during the 80s, some researchers from the academia start looking into this, and they saw that actually we can do this with very cheap components. So everybody can do it. And that's when the real race for side channels started, when they started to evolve and being a bigger threat. And well, that's how they looked back then. If you try to imagine how do they look now, basically they look like this. Just a bunch of code, but in there, you don't have to understand what's going on. But basically, when we are doing secure stuff, when we are doing crypto, we are dealing with secret information that might be one of those variables inside of the red circles or squares. And we have to secure that. We have to compute and run algorithms using those components in a secure way. We cannot have branches that skip pieces of code based on that information, because otherwise it reveals information. Also, we cannot access data based on information from those values, from the keys. So it's not it's not trivial how to perform this side channel proof code. So after said that, I can mention there are different types of side channels. So I already talked about EM and acoustics, but we also have power analysis. By tapping on the energy of the machines, we can measure the power consumption and correlate that to secret information. We have timing. Depending on how much it takes to run an algorithm, we can correlate that to a secret key. And we also have microarchitecture attacks, which have been, if you had heard of Spectre or Meltdown, then you know about them, which can also leak information from your computer. So back to the description. Well, now you know what a timing side channel is. You know what secret-dependent algorithm looks like. Maybe you have an idea. Now I'm going to talk about what's a microarchitecture attack, execution units, and port contention, which is where the meat of the attack is. So a microarchitecture, specifically SMT microarchitecture, is the architecture of the microprocessor running the instructions and operations in a PC. And this is a very complicated, complex machinery with many components, as you can see on the image there. It's often abstracted, so it looks more like on your left. And in there, for a SMT microarchitecture, basically what we have is 2 or more logical cores that what they do is that they share the resources in one physical core in the CPU. So in this way, we can maximize the usage, and we can parallelize instructions. Many of these components are shared, not all of them. And some of them are shared only within one physical core, and some of them are shared within the other cores in the CPU. So typically, we have 2 logical cores in one physical core. And then we have L1, L2 caches, which are just bank memories within one physical core. Then we have execution engine in one core. And then at the very end, we have last level cache, or L3, that is shared among all the different cores. So I don't know if it's visible in there, but basically every time we compute something, the instructions are fetched from either from main memory or the L1 instruction cache or data cache, if they have been cached before. And then they get pre-decoded, and then they are decoded into smaller instructions, micro operations, and then they are put it into the scheduler. And then after that, they are sent to the execution units, where different ports and different execution units are basically taking those micro operations, depending what they do, and then they perform their task, and then they are retired, and that's basically an instruction being done. So looking at that, now I want to talk about the microarchitecture attacks. So since I mentioned that this research has been going on since mid-80s, 90s, and also during the 2000s, and the last 5 years, there have been a lot of research going on this, because they finally realized that, okay, this is exploitable, especially with Meltdown and Spectre. So looking at history, you can see like the first, among the first attacks was in the L1. So that is because that's the closest thing that we have to the CPU, to the execution units. So back then, Intel, so SMT is simultaneous multi-threading that was introduced by Intel in around 2004. And in there, the 2 logical cores share the L1 data cache, so this memory bank. So both have access to this. And one of the researchers saw that 2 processes completely different, if they are scheduled on the same physical core, but they run in different logical cores, they can have access one to the information of the other, and the other way around. So they could leak information through the memory. So he also mentioned that it could be possible to do this with basically any component that was shared between the 2 logical cores. After that, more researchers came, and they decided, okay, this can also be done just looking at instruction cache. So this memory only deals with instructions. The other one deals with only data. And they did it, they proved it. The research continued, and then they attacked the branch predictor unit. So they said, okay, if something is mispredicted, or if something depends on a secret, a branch in the code depends on a secret, then by looking at that branch, we can know if that path was taken or not. And based on that, recover the secret information. So that was done during the maybe 2008, 2009. After that, we had more research on the ports. So in the execution engine, researchers found that by looking at the ALU, we can somehow correlate the secret information to the usage of the LAUs. And then the research started moving out from very specific to one core out to several cores. So that's what they call a cross-core attack. So the first one that was introduced, it was the flush and reload. Basically, this one looks at the L tree. So I'm not pointing out anything in the image there because it's not, the L tree is not there, but it's just arrow pointing outside. That one can be done across cores. So one core can spy on the other core. And starting from there, the researchers just went crazy, and we started looking at different ways that this could be exploited. So Cache Bleed came and said, okay, but there's still stuff going on in the L1 caches. And they proved that they could infer information depending on what's in the memory. And the secret information, it's the secret key and what's in the memory, they can still recover information. And then the TL bleed came. This one leaks information from the translation look-aside buffer. So it's a buffer used to translate addresses from physical to memory, from physical to virtual. So also from there, we can leak information. So there are data and instruction as well. And then, boom, Spectre and Meltdown appear. And they appear because we already had the tools to make them appear. So basically, we knew how to exfiltrate data across the memory. We had different techniques how to perform these attacks. And we did basically the same as what the speakers did on the cards, the hotel cards. They just chained different attacks together, and they came up with Spectre and Meltdown. And then after that, enter us. So what we did, it was Sport Mash. So we went back to the, even like to a lower level, basically to the execution engine. And we look at the ports and what instructions each port, or not instructions, what kind of instructions each port uses or receives and processes. So after that said, I can talk about what port smash is or what we did. Basically, in port smash, we were working on something else through the L3 cache, one of these attacks that I mentioned. And what we did, basically, we have a victim in one core, spy in another core, and then we try to spy one in another. We have done that several times. We understand really well how that works. But then one of our colleagues, what he did is he made a mistake, and basically he pegged the spy into the same core as the victim. And we observed that our traces, they just went very, very large. And we thought, okay, well, this is normal. It makes sense. We have two things running in parallel, and they're just going to be one after the other. They're going to be scheduled, so it kind of makes sense. But then looking closer to the traces, we find out that there was something else going on there, not just the different scheduling. And yeah, this is what happened. And then we start digging into the microarchitecture. Basically, we looked at the execution engines. We knew from previous research that when we have two threads or two logical cores running in a single physical core, what happens is that the instructions are fetched, they get decoded, they get broken down, chopped into small operations called micro-ops. then they pass to the scheduler, and the scheduler just put them in different ports depending on what they do. If they do memory operations, they go to some ports. If they do arithmetic operations, they go to some other ports. If they do crypto operations, they might go to a different port. So we started looking into this and measuring. And what we found out is that basically we can have two threads, two logical cores, issuing instructions that go into the same port, and they will compete to use the ports. But by competing at this, we can create contention in the ports. So one thread can try to get all of the resources, but of course he won't get it. The other thread can try to do the same, he won't get it, but there will be contention. And based on that, we can communicate one thread from the other. So what we did was that, basically having two threads targeting the same port. So there are instructions that target, most of the instructions target different ports, but there are some specific instructions that target one specific port. So what we did is just put two threads issuing the same instruction that would go to the same port. And then since there's only one port that can process that, they cannot go both at the same time, so they have to wait one for the other. And we created a covert channel. Basically, both threads could communicate with the other by just measuring the time it takes to issue an instruction in one port. So if it's fast, you know that there was nothing issued by the other thread. But if it takes more time, you know that there was the other thread in the queue, and then you had to wait for your instruction to be processed. So in this way, they could communicate. So we ran this experiment. This is how one of our traces look like. But this one is just the coverage channel. Basically, when there is no contention, it's one of the lines below. So the latency is smaller compared to when there is contention. So you can see that it's noisier, and we can clearly distinguish between these two lines, which is enough just to create a cover channel in order to communicate from one to the other and to perform a side channel attack. So this is how we first started Port Smash. And then after that, we decided, OK, how do we make it bigger? How can we actually exfiltrate keys from a crypto process or something like that? So for that, I'm having Nicola. He's going to talk about that.
Thank you. So during the process of disclosing this attack, we actually went ahead, and after a CVE was issued for this vulnerability, we actually published a proof of concept to make everybody able to actually experiment and see how easy it is to actually monitor what the other process running in the same physical core is doing. So what I planned for the demo today is to run together this proof of concept, and then we will also look at a live TLS session so that we can actually see what kind of information we can retrieve from an actual TLS handshake, and how we can use that information to later retrieve a secret key for example, with the ultimate goal of impersonating some web server, for example. So let's hope that the gods of demonstrations are with us today. So this is all happening live, and I hope everything works. So the first thing that I have to do, just to make sure that the channel is as little noise as possible, is set up the governor of the CPU to actually run in performance mode so that we don't have frequency scaling, making things smaller or bigger depending on how fast the clock of the CPU is running. And after that, running the proof of concept is just basically running a script, which is not that great for a demo. So what I want to show you before that is what the SPI process looks like. So as Cesar mentioned, what we are using is contention in the ports. And some ports can only execute certain kind of micro instructions. And other ports instead offer a wide range of micro-operation capabilities. So what happens is that if the SPI process monitors the contention on one port, it's able to see some kind of activity in the other process. And if it monitors another set of ports, is able to monitor a different kind of activity. So what we are trying to do here is, by experimenting with different port templates, basically, to see what the SPI process sees, and based on that, pick the correct template that offers the maximum resolution on the kind of activity that the victim process is running. So let's have a look at the SPI process code. So we have another file that is basically just selecting one of the available strategies that we selected. So in this case, by uncommenting this line, I'm telling the SPI process to actually monitor the activity on process 5, on port 5. And if we look at the actual assembly code, what happens is that when this function gets called, it will run in a loop. And the number of iterations in this loop is set by this SPI num timings line. So it's defined in the header file that you can see on the right. And basically, we set a counter, and then depending on the strategy that we choose, we have different kind of assembly instructions that target that set of ports. So for example, if we were using the strategy monitoring ports 0156, we will have 4 additions that will be potentially scheduled in parallel to all 4 ports that are able to solve the integer addition micro-operation. And the port 5, which is the one that we are going to use, is using this instruction, VPRMD, which is basically a vector instruction. And this is a kind of instruction that can only be solved by the electronics that are behind port 5. So by targeting this port, we know that, by targeting this instruction, we know that we are using port 5. And the reason why we have 3 repetitions of the same instruction is because different micro-operations have different latencies. So, for example, this particular instruction has a latency of 3. It means that by the time we issue the first instruction, we have to wait 3 clock cycles for the instruction to be retired and return its result. So by issuing 3 operations, one after the other, we can saturate the pipeline for that port and make sure that nobody else can use that port at the same time, because we are trying to saturate it. And so these 3 instructions are actually repeated 48 times for each iteration of this loop. And the reason why we have this arbitrary repetition is to maximize the resolution of the monitoring. So the reason is that every time we start over the loop, we are running other micro-operation that will update the counter, check if the counter reached the end, and conditionally jump. So we want to minimize the effect of those instructions on our monitoring. And we do that by repeating several times these 3 instructions. OK, so by running make, I just compiled again the SPI process. And in the proof of concept, we are going to run the SPI process on one logical core, and the other logical core will be running a harness that is running it's running OpenSSL code, but is specifically targeting the elliptic curve scalar multiplication operation, which is the fundamental operation that is being run during a TLS and shake, where one of the two inputs is actually a secret scalar. So if we are able to see something in this operation, then we can use that information to retrieve secret scalars and ultimately break the system. So in here, we can see that ECC is the program that is going to run on the other, has been run already in the other core. And the output of the program basically says that we have a secret scalar k, and this is the length of the scalar is around 384-bit scalar. And this is basically, it's not exactly the secret key of the whole algorithm, is just a step. But having knowledge about this will allow us to retrieve the secret key in an elliptic curve crypto system. And so we will come back and look at K in a second, but let's look at the trace that we collect. So timings.bin is the file where we saved our observation on the latency of accessing port 5. And what the harness did was running the scalar multiplication 4 times. And as you can see, we have a very distinguished pattern in the execution of our SPI process that monitors the victim process. And you can see this 4 block of higher activity, and those correspond to the 4 scalar multiplication that were run. I'm not going to show you all of them, and we are actually only interested in the very last part of the sequence, but I can assure you that excluding noise, all 4 of them will be basically identical in the sequence of signals that we collect. So now I zoom in the last part of the second scalar multiplication, and the uppermost graph is what our traces look like when they are raw data. And I'm not very good at reading signals, but this one is definitely not good for anybody, not even my colleagues that are way better than me at reading signals. So we apply different kind of signal processing techniques to try and extract or make information more evident. And you can see that there is less and less noise the more we go downward. And just for aiding everybody, even me, to read these traces, we are marking with these red dots the points where we recognize that there is a particular operation running. So the scalar multiplication is actually executed as a sequence of additions and doublings. And every time we see these kind of spikes, we know that that is an addition. And so, for example, at the very end of this trace, we can see that there is clearly an addition. So you can see here that even without the red dots, you can notice this kind of pattern. You have these 3 or 4 peaks that always have the same kind of width, and they are repeated. And the fact that these sequence of additions and doublings is not constant is a telltale that the code that is being running in the other process has instructions that are run conditionally depending on the value of the secret. So if we can extract this kind of information from the secret, and we can actually reconstruct what the secret was. So in this very example, we have a sequence that ends with an addition. And because of the nature of the algorithm that is being used by OpenSSL to execute this scalar multiplication, we know that a sequence ending with an add corresponds to an odd secret scalar. And as you can see, the secret scalar was ending with B, whose binary representation is 1011. So there's a 1 at the end. That's an odd number. We can run the same thing again. This is, again, an odd one, so there wouldn't be much benefit in showing you again. If odd, odd. I'm sure we can get, OK, this is even. So it ends with 6. So there's going to be some zeros at the end. How many zeros? 1. 1, 1, 0. So if we look at the trace now, OK, no, it was running. OK. What we see is that, again, we notice addition, 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 maybe addition. This is sometimes the noise is too much to actually be reliable. But then addition again, we notice another addition here, but before this kind of low latency, we have something else running. So we know that it's not ending in an addition, and actually by further studying this signal, we can tell exactly that there was an addition and then only one doubling. And what we will see if we were to run again and again this same example is that the ending of the sequence and the number of addition and doublings so we look for the last addition, and then the number of doubling peaks that we have afterwards will correspond to the number of zeros that are at the end of the secret scalar. So we are able to retrieve not only if it's even or odd, but actually how many zeros are there in the least significant bits. And so this is the proof of concept. Now we will run the same thing against a process that is running basically S-tunnel to do an handshake. We have a Python script that will connect to this S-tunnel encapsulated service, and it will capture this same, it will run this handshake, and then we will have the same spy process that we are using here, monitoring that exchange and looking at what the CPU is doing in the same time. So we start by generating a fresh key. So there's no cheating here. I don't know what key is being generated. This is a random key, and I mean, it's not really interesting, but basically we are using OpenSSL to generate a secret key and mangle it and generate a certificate based on that random secret key that we just generated. And then if we run our script, so what this will do is run 3 processes. In one process, we will have the S-tunnel server that has access to the secret key, and it will perform signature generations to solve the TLS handshake. A second process is the TLS client. We are not really interested in what the TLS client is doing because it doesn't know anything secret that we are interested in. And then we have the third process, which is the spy process. So what we want to do is that we want to make the server and the spy process run in the same physical core by using whatever capabilities the operating system allows us to use to set this thing up. And we will see what the spy process is able to see. So we actually run 5 iterations of the handshake so that we can see different traces. OK, so this is the first handshake. And the trace looks a little bit different than before, because before we were only running that specific arithmetic operation that we were interested in. This is part of a full TLS handshake. And the first thing that we notice is that we have two similar block of operations. And this is expected because in the TLS configuration that we choose, we are using ECDH for the initial part of the handshake, and then the digital signature comes because the server needs to authenticate all the parameters that were sent by saying, I am really, I don't know, google.com or amazon.com or whatever, right? So we have two instances of the same operation because we are using elliptic cars for the Diffie-Hellman part and elliptic car for the digital signature part. And so the first of these two operations will be the Diffie-Hellman, and the second one, the one we are interested in, is going to be the digital signature part. So if we look at the end of this, looking at the third, we can see again spikes that are very similar to the ones we were looking at in the proof of concept. And so we can tell there was an addition here, another addition here, another addition. There might be noise, we are not sure, but then again, addition, 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 addition. And we can see that these, let me zoom in a little bit more because this is one of the tricky cases. Okay, so we see that there is an addition and then maybe one doubling. So I would expect that if we look at what the actual secret value was, I would expect it to end in 1, 0. So let's see if we are right. So at the same time, the client is actually a little bit cheating because we are providing it information about the secret key. So it's using this information just for helping us visualize this, and it will back compute or reverse engineer what the secret value the server used was. So we are going to be able to see what the server actually used for computing that operation thanks to this, just to verify what we are doing. And the value here is K, the uppercase K, and it ends with E, which ends with a 1 and a 0, as we expected. We can look at another trace again, and now I will ask you to tell me what you think is the end of the secret scalar. Okay. So raise your hand if you think this is an odd scalar. Raise your hand if it was even. Very good. I also believe it was odd. Let's see. So it ends with B, which is an odd scalar. Very good. So by repeating this thing over and over and over, and basically repeating this stuff is free because if you are google.com, how many handshakes, TLS handshakes per second are you doing? If you are collecting 10,000 of these, you are just a drop in the ocean. So basically, collecting a lot of these traces is basically easy. And you, as the attacker, have full control on when you start doing the handshake. So by collecting a lot of these, what you end up with is a set of equation where you know some bits of the secret stuff that you are not supposed to know. And by using crazy black magic math, you are able to put all these equations together and solve this very complicated system and retrieve the actual secret key. So not this nonce that is ephemeral and different every time you run an handshake, but the actual long-term secret key of the server. So that's, in a nutshell, what we did to demonstrate our attack. Okay. So
by the way, now you can read signals, and you are masters of that, so you can start performing side-channel attacks.
Yes.
As well.
And please, if you were able to read the very top one, contact our university because we are definitely interested in hiring you. So let's talk about countermeasures. It's a little bit tricky because you can, as usual, apply countermeasures at different levels. So the first thing that we have to say is that we are able to retrieve information on what the other process that is co-located to us is running just because that process is running instructions depending on something that is secret. So one very straightforward countermeasure is saying every developer that you shall not execute secret dependent instructions. The thing is that it's totally fair to say this. You can actually say this is a bug, this is a programmer error having code that depends, whose execution is conditional to some secret data. The thing is that we have been repeating you shall not execute secret dependent code at least since 2009 and probably even before. And guess what? After 10 years, we are still seeing in the most widely adopted cryptographic library this kind of code. So yeah, it's fair. And we actually went and fixed this thing, not as a result of this work, but as the result of another work where we were attacking exactly the same code path because of this characteristic. But the thing is that you could say that every single buffer overflow or out-of-bound access, that's just a bug, that's a programmer error. And as an operating system or as a hardware manufacturer, you could just wash your hands and say, that's not stuff that I have to fix. But we know that there's value in actually making the life of the attacker that is trying to exploit a buffer overflow or an out-of-bound access more difficult by randomizing addresses in the stack and doing all kinds of things that we know operating systems are doing. So the next step of the thing, after recommending not to do secret dependent code execution, is going to the operating system and try to figure out if there are ways to prevent this kind of attack. And it turns out that there is one recommendation that we can give, and it's tweak your schedulers. So the inherent problem here is that we are running in the same physical core two processes that are in two completely different contexts. And here I'm talking about physical cores and processes, but the same thing could be physical cores running two processes, and these processes are virtual machines in a cloud provider, for example. And so you really don't want to run two things that are in two completely different security contexts, like two virtual machines from two different clients, in the same physical thing, because you don't want to share resources between things that shouldn't be sharing things. So some operating systems decided to go different ways to try and fix the inherent fallacies of SMT. So for example, in Windows, they tweaked the scheduler so that dynamically, if you have, especially in the cross-VM scenario, if you have two virtual machines and the hypervisor knows that they are two different virtual machines, no matter what the virtual machine is exposing to the user, it could be exposing only one logical core or two logical cores, but the scheduler will make sure that it will be assigned to the full physical core. So you won't have two virtual machines running at the same time in the same physical core. Linux has a similar system. The thing is that, to the best of my knowledge, right now, it doesn't do this dynamically. So what you can do as a system administrator of a provider, of a virtualization provider, is that you statically set the affinity of different virtual machines that might be running different guest operating systems. You set statically and manually the affinity of each virtual machine guest with a specific subset of physical cores. So this is not very robust because, of course, if you have tons of guests, this is unmaintainable. And Of course, the naive solution is just disabling SMT by default. That's what OpenBSD did this June after TL Bleed was published. It's a way to go, of course, but some of the users might not be prepared to pay the performance cost of this. OK, so that was all for me.
OK. Well,
we have to run a little bit.
Yes, for those of you that know what SGX is, well, basically SGX doesn't protect against port smash. So as you can see in there, these are two traces. The upper one is from SGX. The one on the bottom is from outside SGX. They look pretty much the same. So it's also vulnerable to port contention because basically port smash is very low level, so it doesn't care about SGX or not. So now the fun part. So this is recent research that we did at the end of last year. During the 1st of October, we notified Intel about our findings. And then we said, OK, this is what we did. This is our results. We would like to do a proper security disclosure. So first, we go with the vendor. And we tried this in different architectures, Kaby Lake, Skylake. It worked. But we had some conversations with Intel, but they say, OK, this is part of the microarchitecture, so we are not going to fix anything because this is known, has been known since the first SMT architecture. So we are definitely, thanks for the research, but we are not going to do anything about that. And then on the 26th, we notified the OpenSSL security, given that we exploit this in OpenSSL, so they would fix it. And at the same time, Billy notified CERT fee. I think there's some people here from CERT, but basically they help us to get a CVE, vulnerability identifier, because Intel refused to assign one because they said this is not a vulnerability. CERT fee helped us to get that. We also notified different security OS distros about this. Some of them took measures even before, and they completely deactivated SMT at the OS level. Then on the 1st of November, the embargo expired, and we made the research public. And then after that, basically, Twitter went, and Reddit, they went crazy and started giving conspiracy theories about our research. There was an Intel office close to Tampere University of Technology, so they paid us to do some kind of bad publicity to AMD because we said that this might be possible in AMD. We speculate. We don't know, but might be possible. And there was a lot of discussion going on, especially on Reddit. And like experts in Twitter with 140 characters to criticize all your work. That's great. Somebody went and registered the port smash handle and some domain. So I guess they didn't get any money from us, but anyway, they tried. And since we didn't have an AMD machine to test this, to support our speculation, then the people from Dansus in Tampere, they gladly sent us an AMD machine so we could test this. And then during December, we checked AMD, and indeed, even though the microarchitecture is different, so they don't have the concept of ports, but they have some things similar that they are called pipes. They are also separated depending on the kind of instruction. But at the end of the day, the work can be reproduced. If we look at the traces, they look pretty much the same. So we notified AMD about this in November. CERT also, I think, was in contact.
Yes, definitely. They helped us trying to solicit an answer from AMD that never came.
Yeah, but they didn't reply ever. So, and well, the embargo about the results from AMD, they expired yesterday. So this is just like fresh. It just yesterday we were allowed to talk about this starting yesterday. And then we yesterday found out that this week at the CES, the Consumer Electronics Show, the CEO of AMD was there. And then she said many things, but among the things that she said is that security is fundamental. It's a day one expectation that when you buy a processor, it's not going to leak your data. They never replied, so we can still leak data from their processors, but that's what she said. And basically, we got to the conclusions. So we're running out of time. So port smash is configurable, portable, and require minimal prerequisites. Compared to other side channel attacks, they use the memory subsystem. So they all depend on the memory subsystem, but port smash just depends on the port. So even if you don't have memory instructions, you can perform port smash. That's the link of our manuscript if you want to read more details about it, more technical stuff, and more background information. You can check it there. It's public, no paywall, no nothing. By the way, if you're doing research or whatever you're doing, please make everything open, because there are people who are not in the academia, and then they might not be able to look at your research.
Also, this is taxpayer-funded research,
Yeah.
so it's good that it's given back to who financed it.
Yes. So, lesson learned, side channels, they are real. They have been talking about that since the 40s. They are still real, even though people say like, no, they are not, or we killed them, or we solved everything. No, they are still real. And are not going away anytime soon. So just December last year, ARM announced their first SMT CPU core, so the first processor from ARM with multi-threading. So it's going to be interesting to look at that, especially because it's used for automotive. So yeah, it's going to be fun in there. And also, finally, we would like to thank ERC, European Research Council, Nokia Foundation, and CERT-FI for all the help during the disclosure. And that's it for us. Thank you very much.
So if you have some questions, we have exactly 1 minute and 20 seconds to answer them. Let's see what we can do. So there is one in front here.
If not, also we can talk afterwards during the party with some beers.
I guess everything's easy for you guys, but how easy is to get your software running on the same physical core than some unknown target software is running, for example, in a cloud environment?
Okay, so it depends. So one of the main criticisms against side channel attacks that are based on SMT is that how are you going to be co-located in the same core as the process that you want to target? And there is a naive answer to that, that is, we just run enough instances of the spy process to occupy all the physical cores. That's one solution. Also, of course, that's going to be very easy to be detected, probably, because it will affect performances. So what you can do is explore first, so having an exploration phase where you use this approach, with this brute force approach, you try to find where more likely something is happening, and then you monitor only that in depth, for example. But there are different techniques to do this. And in the virtual machine, cross-virtual machine scenario, that's even more complicated. but there are research results that specifically target the problem of how can I make sure I am co-located in the same farmhouse where my target victim is, and how can I try to get in the same course where it's running. So there are ways. Thank you for the question. Any more questions? One there?
Hello. In your presentation, you mentioned that OpenBSD disabled multi-process or SMP, symmetric processing by default, and you mentioned that it was kind of paranoid of them and it hurt performance. And I kind of want to go back and visit that again because I think that's the only way forward. Like, if we're going to have security conscious, if we're going to fix these issues, then we need to have an operating system that says, no, this is not a performance-based operating system, whether it's Linux or OpenBSD or Windows. Like, run your secure things here, but don't run a database here. Don't use this for gaming or whatever, because I think that's one of the ways forward as we're finding more and more security issues in Intel, AMD, any kind of CPU.
Yeah, so that's definitely a good point. I didn't want to at all sound like bashing on OpenBSD for going the easy route of disabling SMT, because you must be bold to say, in a world where every other operating system supports SMT, to say, no, we are not going to support it because it's unsecure, and you deal with the performance side. I definitely get your point. It's true. And yeah, SMT, by its own concept from its inception, it's sharing resources. And there's a side channel every time you are sharing resources among two different things that shouldn't be sharing. So disabling SMT is perfectly legit, but it still leaves the question open of what do we do with the existing server farms, and if I'm Amazon, I don't want to lose customers, and I want to use my machines to the full potential. So if I am buying machines from Intel and AMD, I might want to ask them to provide me CPUs that are performant and secure to at least to their best effort. Okay. I hope I answered your questions.
Thanks.
So I think we are completely out of time right now.
So
thank you very much.
Thank you. It's party time.